Thank you everyone for coming to this seminar. So today we have Professor Jianyu Yuan from the institute called FUNSOM of Suzhou University, China. So Jianyu got his Ph.D. in 2016, and then he did 1 year exchange at the University of California at Santa Barbara. After he got a PhD degree, he was appointed as an associate professor at Suzhou University, FUNSOM Institute. Jianyu's research interest is organic PV and quantum dot solar cells. He's published more than 80 peer-reviewed journal papers with an H index of 25. It's a very good track record. Okay, thank you.
Thank you. Okay, thank you for the kind introduction. Actually, so I'm used to work on OPV, and I'm a rookie on the quantum dot solar cell compared to Dr. Huang. I think she's an experienced expert in this field. So thanks for the invitation, for inviting me here for like a week to Australia. And this is my first time to here. I think it's a very beautiful city in Sydney. So really enjoy it. And today I give a brief talk of our recent work on perovskite quantum dots, which is a very new topic. So first of all, I think last year, Dr. Huang with us, also Dr. Hu Long, to our institute and give us a great talk on perovskite and things have been done here in the UNSW for the most about the perovskite solar cell, so which is very popular in the recent years. And today I will first start a little bit about something about Suzhou and our university, FUNSOM. And also in the second part, I'll give a brief introduction about what is perovskite quantum dots, which is I think not everyone here was familiar with these kind of materials. So in the last part, I will briefly introduce some of this work have been done in our lab in the past 2 years, focused on this topic, perovskite quantum dot solar cell. So first of all, Suzhou. I'm not sure how many of you guys have been to Suzhou before. I see a lot of Chinese here. Okay, good. So Suzhou is quite near Shanghai. So if you take a high-speed train, about take you 20 to 30 minutes. So pretty convenient. If you take a bus shuttle from the Shanghai airport, about like 2 hours from the Pudong airport to the Suzhou. So it's a very beautiful city. You can see from the map, you'll be surrounded by a lot of canals and a big lake here. So we call Suzhou the Oriental Venice in China. So actually it's a very old city, even older than Shanghai. So we have a history of more than 3,000 years. The whole population of Suzhou about I think 12 million here. So probably like 50% of the Australian population. So it's so crowded in Suzhou. And also it's a major city now. I think Suzhou, there's an old city in China called just as there is a paradise in heaven, and there are Suzhou and Hangzhou in city, from which you can see Suzhou is very beautiful. Suzhou is famous for its gardens, I think. So all these, we have, I think, almost over more than 100 gardens. So these classical Chinese gardens, each one have their own style. So in these gardens, everything was well organized. So you can see the smart of Chinese people in the old times. And you definitely, every people go to Suzhou, they will visit one of these gardens. The most famous one called the Humboldt Administration Park Garden. The other the new part of the city of Suzhou is which was built by jointly built by Suzhou and the single government back to I think 1995. So it's very beautiful, very modern city, like the downtown of Sydney. So you can see a lot of buildings over here. Here we call this like Pence Building. So it's very famous in a lot of Chinese TV series. So next time you can go to Suzhou, you can visit the gardens. Also, you can visit the SIP. We call it SIP, Suzhou Industrial Park. So our institute was located in the SIP, in the south part of SIP here, near the lake. We call it Dushu Lake. We have 2 lakes here in the SIP. One called Jinji Lake. Around the lake, a lot of shopping malls and a lot of banks. So it's kind of like a economy center of Suzhou. And around the Dushu Lake, we call a high-tech education park. So there are a lot of universities around in the Suzhou University. The new campus was one of them. They have other campuses like Nanjing University, they have a campus in Suzhou. So probably around like 10 institute or university in the Dushu Lake High Tech Education Park. So our university was the biggest one. And this is our institute. So our dean is Professor Shutong Li. He's a former director of co-staff, which is an institute in City University of Hong Kong. So in 2008, he moved to China and built our university. So he's the founder of our university. Our name was a short name called FUNSOM, called Institute of Functional and Nano Soft Materials. So Professor Li, he's a really good guy, and he's our hero, and he's also a fellow of Chinese Academy of Science, so the fellow of the Solar World Academy of Science, also the associated of SAS Nano. He has a lot of publications. He's a good scientist, and also a good leader. So in the past 10 years, during his great efforts, we have built a very strong team. Now we have like 40 PIs in our group, in our institute. All of them have a very solid background. And we have like 30 professors, associate professor lecturers also in our institute. And we have a strong supporting team of about 20 people. Most of them were like technicians and administration workers. So every year we have include 100 undergraduate students, so which is not very big in China. I'm not sure if it's big here. So the total number of the undergrad students is about 400. So every year we have more graduate students, including master's students and Ph.D. students. Every year about 150. So the total number around 600. So the students number about 1,000. So it's a big institute, but the space in our institute right now is very limited. So we have more space. We can develop to a more more strong team. So what have we done in FUNSOM is that we started from nanomaterials and nanotechnology. We have 4 different directions. So one is definitely optoelectronics. So we've seen work down here. The other about renewable energy. We all do some biomedicine. So also some environmental research. So each direction we have 10 PIs. So that in the past year, you can see that we were established in 2008. In the past year, we have published about 2,000, approaching 2,000 papers, including science and some Nature series paper. And we have enough funding from the Chinese government, also the local government of Suzhou. And based on the FUNSOM, in the past 10 years, we also developed other like platform. Yeah, one of definitely in 2010, we built our institute for our undergraduate students. So it's one of the 17 pilot college, which was issued by the Minister of Minister of Education in China. So they give a lot of money for for the promotion of these undergraduate students, because every year we can have only 100 students. So they were kind of like a field to try different style to promoting this undergraduate student compared to the conventional institute. We also have a national center we call a collaborative innovative centers, which also I think it's all for the minister of maybe the education. So, but this program was ended 2 years ago because we changed our leader. So FUNSOM is we currently we're not a state key lab, but we are a key laboratory of the Jiangsu province. So we are on our way to our state key lab because it's very competitive in China if we want to be a state key lab. Sorry. So I think 3 years ago, this is what Professor Li wanted to do. He built an industry park near Suzhou. It's in the Wujiang city, a city around Suzhou. It's we call it Institute of Organic Optoelectronics, so called a IOO. This institute have a lot of functions. Mostly they want to industrialize the technology have been developing in our institute. They also have provided some platform for the students who want to run a new company, a small company. So it was built like 3 years ago. I've been there, so it's very cool places, very cool place. So also we open for new positions. So anyone here was interested to find a job in China, so you can check this website, our website. So I think most of these directions were quite affiliated with the research done here, and they give you a good package here. Sorry, just don't translate into English, so just copy from the website. So they have pretty good pay and a pretty good research funding. So if you're interested, you can just check this website and shoot us an email. Okay, so back to today's topic. So perovskite quantum dots. So I know Dr. Huang, he did some research on or the experiment for this perovskite quantum dots materials. I'm not sure if you either guys was familiar with this one. So why we want perovskite quantum dots? So since you can see that for the thin film perovskite, or called bulk perovskite solar cell, they have very good performance, right? The efficiency is very high, over 25%. So for the other very important kind of material we call it quantum dot solar cell, quantum dots. So the most famous one we call it PBS, the laser sulfide. So laser sulfide research in the past decade, I think the efficiency right now is about over 12%. So the stability is very well compared to perovskite. So that's the key. But we want to also emphasize the advantage in the quantum dot device that the processing is more advantageous than the perovskite bulk film. You can use industrially friendly solvent to process this quantum film. You can do a layer by layer processing. It's ideally for like large scale fabrication. Also, you have quantum confinement effect in these materials. You can adjust the size to turn in the optical properties of these materials, which cannot be realized in the bulk film. So that's the reason why I combine these together. We want to develop we call it perovskite quantum dots. We're not the group in the world, only the group a lot of few groups on this, in the world working on this one. But we just started about 2 years ago on this topic. We call it perovskite quantum dots. So we just want to combine the advantage of the PBS quantum dots to this bulk perovskite solar cells. So from this figure, right now we are working with a review paper with Jianyu Yuan from National Renewable Energy Laboratory. So last time I visited his lab for some discussion about this kind of research. So the perovskite quantum dots, actually it's first seen by Kovalenko in 2015. He used the Hall injection method to synthesize first all inorganic perovskite quantum dots, the cesium layer-based bromine chlorine or iodide. So you can see from the TEM image, you can see all these quantum dots were well organized. It can form the superlattice. So you can also stabilize this ideal the black face of the cesium layer iodide in these quantum dots. You can also see the quantum confinement effect in these materials. Even is not so strong because it's totally different compared to PBS. So, but you can still see this window here. You can adjust these optical properties through changing the size of these perovskite quantum dots. So Jianyu Yuan first reported the perovskite quantum dots for solar cell research in 2019 in this science paper. And I think the amazing thing for these quantum dots is that they have like called an ion exchange. So even people see it in the bulk film, but it's more significant in these quantum dots at the solution state. For example, for these cesium layer-based perovskite quantum dots, you can change both the A side and the B side cation with this exchange process. For the halide, so it's very fast. You can form like 100% halide exchange at the solution state. So you prepare like cesium layer bromide, you can put like put like layer iodide in the solution. You can just heating or stirring. You can change to cesium layer iodide. So it's very easy. You just have one material in hand. You can create different kind of materials. So this is very interesting. You can also adjust these optical properties if you want to make a solar cells. As I mentioned, Dr. Lucer, he's the first guy who used this material for solar cell application. So in 2016, he first reported use a method. He used methyl acetate to stabilize these quantum dots in the black phase, we call cubic phase. And also he used the same method to remove this ligand from the surface to prepare a highly conductive film for solar cell fabrication. And then he used the other treatment, we call it here he used the FI treatment, the organic kite here, different kite, but the FA should the best performance. So he can further improve the mobility of this quantum dot film, and he can get a certified efficiency about 13.4%. He also participated to realize how this solvent can remove this ligand and passivate this surface. So if you take a look at this certified PV result from the NREL, I just take the perovskite bulk film and the quantum dots. So I'm really excited because last week the new record came out about 25.2%. So it's very fast. The efficiency goes up very rapidly for the bulk film. But if we take a look at the quantum dot devices in the past decade, before 2016, you can see all these results came from the PBS, most from telesurgeons group at Toronto University of Toronto. But after 2016, you can see the new number, 13.4%, come from Joey Russo's work from NREL. They use the cesium native iodide quantum dots to achieve a record efficiency. And last year, I think Professor Jianyu Yuan from Queensland University, they reported the highest record about 16.6%. But the paper didn't come out yet, so I think this result should be also like perovskite quantum dots. So from this figure, you can see the perovskite quantum dots maybe open a door for this quantum dot solar cell research. So efficiency jumped from around 12% to over 16%. So that's a very big improvement. So also have a lot of space because just started this kind of research. So okay, in the last part, I will talk about the research we have done in the past 2 years in our group, in our team. Now, so we have a lot of people, about 7 to 10 students working on this topic. So we do a lot of synthetic work or the device work in the past 2 years about perovskite quantum dots. So based on these perovskite quantum dots, we get a lot of lessons from that because we used to work on the PBS, not me, our group. So we a lot of lessons learned from the PBS. We try these 4 different aspects. Actually, we don't start with all of them, but we most focus on this post-treatment and device engineering. We just studied about the synthetic work. So we try different aspects to improve this performance of the quantum dots, mostly efficiency definitely, because if it goes up to 20%, so there'll be a lot of people will feel this more attractive. Also the stability, we won't try to review if this material was more stable than this bulk film. So you should prove to the people, to this community about the advantage of these materials. Otherwise, people will not jump this field. So I'll generally brief for these 4 different parts. So the first one actually for the composition control, as I mentioned. So the cesium native bromine iodide, the stability is not very good. Even it's much better than the bulk film. Cesium native iodide bulk film. It's not very stable. When you take out from the glove box, the color was suddenly changed to like yellow, from black to yellow. But iodide is okay, but it's still not very good. So we try to mix the bromine into the system to lower the phase transition temperature. Then we try to get a more stable quantum dot film. But our first one, we need to make a cesium, very high efficiency cesium native bromine devices, because if you change these halides, so actually the quantum dots devices, they have different, this is very ionic, so the bonding of this ligand is totally different compared to PBS. So once you change one atom, the bonding also significantly changed. So we use the same method to treat the cesium native bromide film. We cannot make a device. So we develop a new method. We use a more stronger solvent called acetone, and also combine with this this inorganic salt to remove the ligand. From this characterization, you can find this surface this long ligand chain was mostly removed from this film. You can also from the PO, you can see the film was well passivated. So actually the efficiency of this cesium native bromide not very high, because they have very large band gap. The absorption you can hear about 550 nanometers. So the efficiency around 5%. We still improve this system. I think it's easy to get a 5%. But for the thin film, the cesium native bromide, the efficiency should be around 10%. So they still have room for this system. But use this quantum dot film, we find it's not totally different compared to the solid bulk film. The color is different. We don't know why, but the stability is very good. You can see the stability. We test even the efficiency very high, but we can find this kind of quantum dot material can be an ideal material for a tandem or solar concentrator, even for the semi-transparent solar cell. And for the in-situ passivation, we right now we just published one work on this system. We just started this research for the synthesis. we mostly want to change this ligand condition at a solution state. Then it's easier to make a very high conductive film. So we use this. We just borrowed this concept from the thin film. I think also, I think Dr. Huang has published some papers on the doping of this inorganic quantum dot film. So we just borrowed this idea. So you just try, because for the Perovskite materials, they have a high tolerance to these defects, but actually they have defects, either the lattice defects or the surface vacancies. So we use this PB terbium doping in the synthesis process to dope the film, to dope the quantum dots to achieve a better quantum yield, and also want to decrease the trap states induced by these surface or the lattice vacancies. This kind of doping concentration actually don't change this the quantum size and distribution, so that's very good. Also, we find the optical properties of this film is not changed significantly, but the quantum yield was improved to approaching 100 to about like 90%, which is very good. So we also use this quantum dot to make a thin film. So we can see the slight enhancement in the GSC finally can get an efficiency about over 13%. And mostly when you dope use these doped quantum dots, you can have a more stable quantum dot film, and the device is more stable in the ambient condition without any encapsulation. As I mentioned, we do a lot of work on the post-treatment and also device engineering. So I will talk more about this kind of work in our lab. So we, for these quantum dots film preparation, so normally we need to remove this long ligand, like oleic acid or oleic amine. So when you remove this ligand, you have a lot of vacancy on the surface. So you need to further passivate these vacancies or fill these vacancies. So we do the XPS of this film. We find that there are a lot of like vacancy of the cesium, the A side vacancy in this ligand exchange film. So which will induce this recombination in the film. So we just use a very simple method. We select a series of cesium salts with some organic or inorganic salts. We try to prove a concept that we can use a cesium ketide to passivate, to fill in this vacancy and passivate this surface. So it's a very easy idea. So we just try on the device. So actually it works very well. So we tried all these cesium salts. It works for these devices. Cesium acetate show the best performance from the original around 12% to over 14% PCE. So it's very simple surface treatment, but it gives you a significant enhancement in the device performance. So at that time, this is the highest report for the cesium lead iodide quantum dots devices. We also do some characterization. We find when you use these cesium salts to treat this surface, the ratio of these elements is more ideally compared to ABX3. So we have like vacancy of the cesium. More importantly, so if you passivate the surface, the electron coupling between the quantum dots was enhanced. That you can see from these mobility measurements, you can see we have an enhancement of this mobility. You can also calculate these free carrier diffusion lengths. You can see use this cesium ketide treatment, the free carrier diffusion length was significantly improved. We also do the transient absorption measurement. You can also see we have some decreased combination in this surface passivated quantum film. So it's a very simple and a very efficient way to further improve the performance of the Perovskite quantum dot solar cells. If you're working on this quantum dot solar cell, I think you will face the same issue as I show here. So normally, when you treat this film and then sprinkle the top layer, sometimes it will dissolve the bottom layer. So actually, I think there are a lot of reasons for this accident. But for personally, I think they have two main reasons. The one is that the quantum dots you synthesize is not very well enough. The other, when you do this surface treatment, use methyl acetate to remove this ligand. So sometimes it cannot be as very efficient because for these really bad or really poor quantum dots, the surface ligand condition is really complicated. So if you one-step treatment, it's costly to remove all these ligand. So if you treat it for a longer time, they will do like phase transition. So either too short or too long is not a well controlled uses the method. So here we developed a method to mixing some amine in this methyl acetate solvent during this treatment. You can find this film was you can see you can achieve like very good film compared to the up panel. So for this film, just when you deploy in the top layer, you're dissolving the bottom layer. We use this amine to mix to dissolving. We use very tiny amount, very little. Here you can see the volume ratio here, 0.5 to 3,000. So very much. But if you use more, you will be cause like phase transition in this quantum dots film. So from this characterization, you can see that the surface of this quantum dots is more clean compared to pure methyl acetate treatment. So this gives you a more reproducible device fabrication. A lot of people can repeat them. From this figure, I can show the device results. You can see here, from here, this one. So we use, for the control device, you can achieve about 13%. But if you use this, mix some amine methyl acetate, you can achieve to over 14%. That's not very attractive. But here, you can see from this figure. So we use a very poor quantum dots. So sometimes the students do not have a good skill when synthesizing quantum dots. This batch, they has batch-to-batch variation. So you have very poor quantum dots. So normally you can get like around 10% or even lower, 8%. That's the people why I don't want to do this kind of solar cell. So you need to first synthesize the quantum dots, the purification, and then you use the quantum dots for the device fabrication. It's much complicated compared to the bulk film. Bulk film, you just put the precursor in the solvent and just do the spin coating in the anneal film, right? So we want just to show people how to improve this reproducibility of these quantum dots. So you can use this different treatment to get a more clean surface. Then it can increase the coupling of these quantum dots. It can further improve the efficiency. So here you can see from around 10% to also over 14%. So from these two figures, you can find use this method, you can achieve like more efficient and more reproducible quantum dot, cesium data iodide quantum dots, which I think is very important to this community. And recently, we also show you further the strength of solid state engineering of this surface of ligand can further boost the efficiency to over 15%. This is for the pure cesium data iodide. So it's almost, I think it's maybe almost compared to the bulk film. But we show some interesting here. We can show very high OVOC over 1.2 eV. So here in our lab, we use interfacial engineering. We can achieve 1.3 volt for the cesium data iodide. It's super high. And also you can see the GSC here is about 16. There's still room for that. Right, for the bulk film, I think cesium data iodide, they can achieve 19 or 20 the GSC. So we still have room for the cesium data iodide quantum dot solar cells. I think maybe 17 or 18 is very possible in the next maybe 1 or 2 years. The last part, we do some work on this device engineering. Because I'm a device guy, I do most of my work for the device optimization or characterization. I don't do a lot of synthesis. We have a team in the lab to working on the synthesis. So this is actually our first project for this cesium data iodide perovskite quantum dots. We published about 1 year ago. So here, because I'm used to working on the organic stuff, so I'm working on the OPV. I do a lot of synthesis on the conjugated polymers. So we have a variable this organic semiconductor in our lab. So we can choose different one based on this energy level or this mobility, to using as an interfacial layer in this either perovskite bulk film or quantum dot solar cell. So when we optimize, first try to repeat the Joey Russo's science paper, we find it's very difficult because if you spin coating a spiral on top of these quantum dots, use a carbenzene, so it's very strong solvent. So we'll be dissolve this bottom quantum dots layer. So we try that because also for spiral you need to oxidization to achieve, or doping to achieve higher mobility. So we try to repeat that structures, but the efficiency about 6-8%. So it's not, we try different efforts, but right now we can get like over 10% use like pre-oxidation the spiral solution, but it's still not very high. I also talked to Joey about the structure. Maybe we use different TiO2 here. He uses Suzhou TiO2, but we use a hydrothermal method to get this TiO2 layer, because I think for this quantum dots purification, you need to very dense film on the bottom. The Soochow method, maybe you need to. We have tried that method, but it's not very highly reproducible. So here we use different conjugated polymers to want to replace the spiral, because for these conjugated polymers you need to dope them. You can choose these different polymers according to the energy level of these quantum dot materials. So I just show here, this is 3 commercial available conjugated polymer. So we have different style. We can also do the optimization or the chemical modification on the structure. You can tune this energy level to match your quantum dots. So I think it's very easy and very efficient way. So we can show the results here. You can see for the spiral can only get around 10% and show a very large hysteresis. But for these quantum dots, right now we don't know why, but we still don't show any significant hysteresis, but efficiency also over 12%. So at that time, it's a very good result. And we also do some characterization. We do the GWAX for this 2D X-ray for this quantum dot film. You can see for this pristine quantum dot film, just you synthesize film from these synthesized quantum dots, you show highly crystalline properties. You can see these different diffraction dots here, showing these quantum dots are highly crystalline. But when you do the ligand remove, you can find this film where the diffraction peak is almost similar. So the coupling of these quantum dots is not very strong. So you have also interspace. So further maybe improve the coupling of these quantum dots, you can have like better transport. Maybe show higher performance, especially for the GSC. And in this work we have shown a VOC about approaching 1.3 volt for the cesium layer island. So it's very high. If you use the optical band gap to calculate the VOC loss that people did in this community, you can see the cesium layer island at that time it showed the lowest one. I know the paper came out this year from Jinsong Huang's group. He used different some benzene derivative to passivate the bulk film surface. He can achieve like a VOC loss about 0.3 something. Yeah, also it's very high. So I think the VOC we have a lot of room for improve the VOC. When you reduce the VOC loss, you can theoretically have a high efficiency for the perovskite, either for the quantum dots or for the bulk film. And also prove this concept can be realized in the PBS quantum dots. As I told before, I'm very good at doing this kind of stuff. You can modify this backbone or either backbone or the side chain structure of these conjugated polymers. So here we show a case that we use a series of polymers. They have same polymer backbone. We just change the side chain here. We do different substitution. We use fluorine, sulfur, and silicon. We try to optimize this energy level on the mobility to match up with PBS quantum dots here. And I also want to show the mechanism of this HTL compared to the conventional like PBS EDT. So we use this 4 polymer. Actually, you can see they have a slightly different optical properties, but the most difference comes from the energy level. You can tune this hormone level or this female level of these mature polymers to match up with the PBS. So from this device performance, you can see because here we use the solution. We use the solution phase ligand exchange method PBS quantum dot, just one-step synthesis, one-step fabrication. So also in just spin coating the polymer on top of the PBS. You don't need to anneal them, you don't need to oxidize them. So it's very easy. It's also very scalable to large-scale devices. The best one right now can achieve about 11.3%. And see at the same condition for the PBS EDT, you can get a 10.8%. Yeah, if I remember correctly. So they're pretty comparable. If you think about this processing of this HTL, I think it's more easier. It's also this concept can be also we have proved in the perovskite quantum dots device, PBS quantum dot. You can also use the PBSC or that other quantum dot devices. So it's very easy. So you can just buy this polymer. This polymer also this template polymer PBDBT is commercial available. So if you want to make an easy fabrication of your quantum dot devices, you can use this method. I think recently there's a Korean group. They use the organic HTL. They can get like 11.5%. and a very high stability in ambient conditions. So they just submitted the paper. So we're almost done this work. So because I just want to try to connect my previous work to the quantum dots. So the easiest way just use this material for like interfacial layer. So we tried this before. We tried this recently. So hopefully next time we can use more in other system. And still, as I mentioned, the stability of this cesium nail halide quantum dots is not very high enough, and also the efficiency needs to further improved. So the problem about the cesium nail halide is its non-optimal band gap for a single junction. So the optical band gap for the cesium nail halide is about 1.73 or 7.75. So absorption about around 700 nanometers. So you can see the GSC here for a control device is not very high enough. Even they have enhanced electrical coupling. But for the perovskite quantum dots, they have a very easy way. As I mentioned, you can do Kai-Tai or ion exchange. So you don't need to synthesize the new materials. So when you have a material in hand, you do like this kind of exchange process. You can develop a new material system. So for this method is already reported by other group. There are a lot of synthetic work on this kind of method. You just mix some, you prepare Fa layer halide to mix together with the cesium nail halide. You can prepare this quantum dot alloy. So even this transition cannot goes up to 100%. But I think the maximum Joey Russo have shown in his SS Nano paper you can do like exchange from 12% to 75%. So this ratio cannot be realized in the bulk film. In the bulk film, mixed Kai-Tai. So normally, this portion is very small compared to MA or cesium. So most of the MA, the cesium and FA is ratio is very small. But here you can have a large ratio of these FA in these quantum dots. The FA is a good thing that you have narrow band gap. So for the quantum dot film, the band gap can lower to 1.55 eV. So you can extend your absorption to over 800 nanometers. But when you change this organic Kai-Tai here, it's larger than the cesium, much larger. So the crystal structure will be changed significantly. So they also change the surface ligand condition compared to cesium because it's not totally different from the bulk film. So use different crystal structures. The ligand in this solution state is kind of like dynamic process. So it's not like PBS is bonded to some of these atoms, but I think it's dynamic process. So all this process will be a significant change. So electron coupling in this FA layer halide is not as good as the cesium nail halide, but it shows very good stability. I think mostly because about the surface ligand. It cannot totally remove this ligand, so this is still protected by the ligand. So the stability and ambient stability is very good compared to cesium. Like we show the two figures here, the IV. You can improve the GSC, but you can also improve the stability. But the VOC is decreased, so the overall the efficiency is almost similar. But they show different advantages. So we try to combine this advantage of two materials to maybe to improve the efficiency and stability of the cesium layer halide. So because as I mentioned, the quantum dots fabrication, they have layer by layer process. So when you depositing the bottom layer, then you do the surface treatment, then remove the ligand. You will not dissolve in any solvent. So you can fabricate the top layer. So you can do layer by layer without dissolving the bottom layer. So this is very interesting. You cannot do this with bulk perovskite film, right? So so we use this concept. We just use the bottom cesium layer and the top FA layer layer. It comes like a tandem structure, but actually it's not a tandem structure. You don't have an interconnecting layer here. So we want this structure can improve the absorption. You can from the optical properties with two different kind of materials. The energy level is also well matched. So we hope this structure can improve the light absorption. They can contribute to the GSC, and also you can have like protection of these use the FA to protect the cesium. You can improve the FA have a better thermal stability. You can protect the bottom layer, so you can improve the stability. So that's our initial plan. But during when we finish this, we almost finished this draft of this paper. So I think Joey Russo do the same work. It just published in late in June maybe. Yeah, it came out in the Nature Communication. So actually, I know the story about this paper. So, but when I visit us, they don't tell me they have to do the same project. So when I come back, I do the same project. I ask them to help me do some characterization to explain some dynamic process. But they told me just submit the paper. So actually, they did this work like about 1.5 years ago, and they can achieve a steady output about 15.2%. They gave a certified result from NREL about 14.5%. So it further improved their previous 13.4. But when they hold Professor Wanli Ma from Queensland, they get a 16.6%. So they just submit this paper. They don't show the certified results. Actually, I think this is a really good paper. So he planned to submit to some maybe Nature Science. But when Queensland result came out, so they just want to just publish this paper. So they just take like 2 months to get it published. It's very quick. So they use a little bit different because use a graded quantum dots. They don't use a pure FA. They use a cesium FA at a different ratio at the bottom layer. Then the bottom is a cesium layer because they use different methods to synthesize these quantum dots. So energy level is a little bit different. Structure also slightly different, but the concept is the same. So you use the gradient structure. You can create a heterojunction within this active layer. You can. They do a lot of characterization. I think it's very good work. You can read the paper. So it's better for charge separation. So you can more efficient. You can see the GSC was significantly improved to about 20. So this is very high. So, but as I said, they have very large hysteresis in their device. For the reverse scan, they get over 17%, 17 point something percent. But the steady output about 15.2. So let's show our results. So we as I told, this is two pure quantum dots. They show a similar result, but when you combine them together, you can show very high, significant improvement to over 15%. We don't have any hysteresis because maybe the TiO2 we use hydrosomal method. So the steady output is similar compared to Luther's work. But when we finished the draft, the paper came out. So we just submit to ACS Energy later. We recently just get the comment from the review and just revise. Hopefully we can publish this paper in the future soon. So from this figure, I summarize the recent publication about related to perovskite quantum dots right after 2016. You can see a lot of paper more than we still miss Joyce's Nature Communication or Jianyu Yuan. They recently published an advancement paper for the pure FA layer island. It gave over 13%. So this community, I think, is become more and more popular. A lot of people join this community because a lot of people doing synthetic work. So also quantum dots material, they have very unique advantages. So maybe you can in the future you can develop some other concept devices use these emerging materials. Okay, I think this is all my talk, so I will stop here. But for the last slides, I will give some perspective about the perovskite quantum dots as we right now working on a review paper on this topic. So I think definitely a lot of people have do the lead-free or team-based perovskite nanocrystal just for the synthesis or for the LED. But no one has did it for the perovskite solar cell, quantum dot solar cell. I think this will be maybe the next step because the issue of the toxicity of lead in either bulk film or the quantum dots should be solved if you want to push this technology to the market. And also definitely I think this part is very, very important, the surface chemistry. So that people have proved this in the PBS or other quantum dots system. The surface chemistry, either in the solution during the synthetic process or for the solid state treatment, is very important because if you want to get a highly conductive film, if you want to increase the electron coupling between this quantum dot to quantum dot, you need to decrease the interspace between these quantum dots. You also need a very short ligand to improve the charge transport from dot to dot. Also, the other part is a tandem cell. So as I said, the cesium layer iodide they show non-optimal band gap about 1.7 eV. It's not ideally for a single junction, but maybe it's good for the tandem devices. So right now we're working some project to use some organic near infrared subcell, because right now if you familiar with organic solar cell, the single junction efficiency about over 16%. The organic material is environment friendly material. They don't have any metal. So they also recently, due to the development of the long fluorine, we call long fluorine acceptors, the absorption of this organic substrate can extend it to over 1,000 nanometers. So if we combine these two substrates together, so maybe I think the tandem cell will be more efficient compared to the single junction cell. Also, you can, that's for my perspective, because I'm used to working on the organic polymers or molecules. So maybe we can create this concept has been previously reported in the PBS. So we can do some different concept solar cell using the hybrid system. So maybe you can find some more interesting fundamental science in this hybrid system. Okay, I think I will stop here. So I would like to acknowledge my team members. Definitely, first of all, our team leader, Dr. Ma. He's also my supervisor, Ph.D. supervisor. He's working on the PBS, but I'm not. I used to work on the OPV. So after I graduated, I found a position in our institute. He suggested me to do something different. So that's the reason we developed this Perovskite quantum dots. But we just did it for 2 years. We still have a long way to go. I will thank all these students for both synthesis and device fabrication, and also our collaborators who help us to make our work more interesting. And also, I would like to thank you all for coming and kind listening. And I will be happy to take any questions. Thank you.
Comprehensive presentation.
Thank you.
It's really, really helpful to us. So any questions from the audience?
You mentioned the terbium doping of some of your
Yes.
cesium lead iodide, I believe.
Yeah.
So terbium is a 3+ cation.
Yeah.
What do we know about where it's inserting in the perovskite?
So actually, we borrowed this idea from this paper. So a lot of people do the synthetic, but they don't do it in the cesium lead iodide system. They do the cesium lead bromide on the chloride system. So I think I think they claim that this 3+ will go to fill in the vacancy of lead. Yeah.
So it's a substitutional defect.
Yeah.
Substitutional
I think so. Yeah.
terbium. Okay.
Yeah.
Thank you.
Yeah, actually, I have a question down the same line. That this is you show the one slide that this doping level is really, really high, right? Like
this is the ratio of the precursor. Actually, we calculated the doping level from the XPS. So even you adding more, but it not goes in the 100% into the crystal. So we calculated from this one. I think 20% is optimal. So the doping ratio about around 2.7%. Yeah. Yeah, just the ratio of the precursor you add into the system. Yeah.
Okay, right. So in general, actually, this composition is a big issue, right? So when you also talk in one slide, it's like you use some kind of ligand change that the cesium and lead and lead and iodide, this ratio, right, is getting closer to this theoretical, 100%. But it's still quite low, right? So you see this lead. Is it really accurate? Do you think that's
that's a really good question. So actually, we do the XPS. I don't trust the XPS sometimes. So because especially for the quantum dots, for the bulk film, I think it's okay. But quantum dots, as here, so even show these cartoon pictures, I think it's nicely show how to remove this ligand, but just we drive this by our hand. It's not from the characterization. So this still have ligand attached to the surface. So it will be affect this like XPS characterization. So we compare the result from the different papers. Now different papers they have different atomic ratio of this cesium lead iodide. So that's a really good question. I think so, but I'm not a pro in the XPS. So we just compare the two films. We use different method. We tell the trend tell the change of this after or before treatment. So for the accurate ratio, I don't know. Yeah.
This is something nice, right? Something a good direction to kind of achieve a better compositional control, right? I think that's something like waiting, like more researchers to do a better job, probably.
Okay, that'll be nice.
Yeah, nice.
More questions? So So I have one question. Have a lot of questions.
We can talk about later.
Well, a simple one is you mentioned that the current GIC is 16, roughly 16
Yeah.
milliampere. And I noticed your film is roughly 400 nanometer. It's sort of similar than the bulk perovskite solar cells. So why did you use thinner? Yeah.
So actually, we try thinner film about 200 nanometer. So the GIC actually is similar, but the fill factor is low. We also use a very thick film up to 800 nanometer. The GIC is high, but fill factor is also low.
Okay.
Yeah, so just kind of optimization, we use this condition. So
it's possible to increase the current by increase the absorption.
Yeah, I think so. I think we need to increase electrocoupling, improve mobility, can get a thick film. Yeah, that's for sure. Yeah.
Okay, very good. So if there's no other questions, let's thank Jianyu again.
Thank you.